Now let's talk about the electronic structure. An electron is confined in a specified region, let's say specified volume around the nucleus, giving it a particular energy. So assume this is the nucleus. The electron will be found in areas, volumes of spaces away from the nucleus, outside the nucleus. We usually start by counting those energy levels from the one closest to the nucleus to the one outside. But those shells, we call them shells, they are the ones that carries rooms where electrons are found. We call them orbitals. And so electrons are always outside the nucleus. To remind you, we said the nucleus is positive because in the nucleus we do have protons which are positive and we have neutrons which are neutral. So that makes the nucleus overall positive, and so electrons will be dancing around the nucleus, if possible, in pairs. If possible, in pairs, with the very first shell carrying only 2 electrons. So you get what we call electron clouds, which occupy a larger volume around the nucleus at a particular distance from the nucleus. So we say at a particular energy. Okay, the region occupied by electrons are called principal energy levels or just shells. So like I said, if this is the nucleus and I have these circles which are the shells where electrons orbit around the nucleus, just like planets orbit around the sun. So we are calling these circles the principal energy levels, or we can go further and say principal quantum number in physics, or you can just call them shells. And they are given a value of n because starting from the one inside, you count 1, 2, another circle will be 3, another circle will be 4. So the principal quantum number will be n. Principal quantum number correspond to principal energy level, and we call it n. The farthest the electron is from the nucleus, the easier it's gonna be lost to another element. So the energy shells are numbered 1, 2, 3, 4, as I've shown with the red lines, starting from the one closest to the nucleus. Electrons in the lower numbered shells are closer to the nucleus, so you start numbering from the one shell principal energy level or shell closer to the nucleus. So electrons in lower numbered shells are closer to the nucleus and are stable. They are lower in energy, they are not easily lost. But the one that is farthest from the nucleus, for example the electron found in n equals to 4, that one is easily lost. Electrons in higher numbered shells are farther from the nucleus and are higher in energy and are easily lost from the atom. Remember, the nucleus is positively charged, the electrons are negatively charged. So if the electron is so far away from the positive charge, is loosely bound to the nucleus and is bound, or it tends to be lost from the space of the atom. So we repeat our statement again. Shells with larger quantum number, for example N56, are further from the nucleus and can hold more electrons because, of course, their radius is larger. So if you have a nucleus again like this, and I have shells around him. So let's say I have this shell n equals to 1, and you have more shells, and then I'm going all the way out there and say this is n equals to 6. You can see that the distance, what the atomic radii or the radius there is going to be, so the radius here is going to be bigger than the radius here, the distance there. So what you are saying is that shells with larger n numbers, like n equals to 6, they are farther from the nucleus, and because they are bigger, those shells are bigger, they can hold more electrons. The maximum number of electrons in each shell is given by the formula 2n squared, where n is the shell number. Let's do that example. So again, pretend that this is your nucleus, and then let's just draw circles. So this is n equals to 1, and then I'm just gonna draw in complete circle n equals to 2, in complete circle n equals to 3, in complete circle n equals to 4. So those n's are principal quantum numbers and correlate to the number of energy levels. So if I want to know how many electrons are gonna be in n equals to 1, I'll use the formula 2n squared. So 2 times 1 squared equals to 2. So the first shell can only carry 2 electrons. What about the second shell? Let me use green. What about the second shell? How many electrons can second shell carry? Use 2n squared. So it's 2 times n equals to 2 squared. That's gonna be 2 times 4 equals to 8. So the second shell, if I would complete it, is gonna carry 8 electrons, and usually they are paired up. You get the idea. And so you can do the same thing for n equals to 3. N equals to 3, so it's 2n squared is 2 times 3 squared, and that is 2 times 9. That's gonna give you 18 electrons. So remember, this one we said it will be 2 times 2 squared, that was 8 electrons. And this was 2n squared is 2 times 1 squared is 2 times 1 is equals to 2 maximum electrons on that shell. The fourth one will be 2n squared is 2 times 4 squared is just 2 times 16, and that gives you 32. So you increase the number of electrons as the radius of the shell increases. I think you get the idea, and you can predict the number of electrons in the shell using the formula 2n squared, where n is the principal quantum number of the shell. Now, the shells themselves in there are divided further into sites that we call subshells, identified by the letters S, P, D, F. And these can further be divided into an orbital. Okay, so now the S contains just one space where the electron can be. The P contains 3 spaces. I call them spaces because the orbitals are the spaces or area or the volume where you're likely to get an electron. So this one consists of 3 orbitals. So now I can call these 3 orbitals. I can call this one orbital, which is the spaces where electrons reside. The D is gonna have 5 of them. So I'll try split this into 5. So D subshell has 5 orbitals, and then the F, you got it right, it's gonna go to 7. So we have to divide it 7 times. 1, 2, 3, 4, 5, 6, 7 orbitals in the F subshell. Now, the first time you're going to see the P orbital is gonna be in n equals to 2. The first time you'll see the D is when n is gonna be equal to 3. The first time you'll see the F is when n equals to 4. The first time you see the S is when n equals to 1, but you still see the S in second shell, in third shell, and fourth shell. So the first time you see it, you'll continue seeing it from that point onward in other shells. So this is just exactly what I've drawn here as boxes. Okay, so who is the closest shell to the nucleus? The S orbital, because if this is the nucleus, we say that the first shell, n equals to 1, will carry a maximum of 2 electrons. Okay, so this tells me we have a maximum of 2 electrons in n equals to 1, and those 2 electrons, they will be in the S orbital. Electrons are represented by fishhook arrows facing opposite because electrons are equally charged, so we have to put them opposite, like you put two magnets opposite, north, south, south, north. So the first time you'll see the S will be in n equals to 1, but again you still see the S in n equals to 2, only that you're going to call it 2s. So I'll have you know that the S shell will carry a maximum of 2 electrons. This is me giving you more information. The P has 3 shells. Each orbital carries 2. P subshell has 3 orbitals, so it will be 3 times 2 electrons. P will carry a maximum of 6 electrons. The D has 5 orbitals, so each orbital carries 2 electrons, so it will be 10 electrons maximum in D. The F has 7 orbitals. The F subshell has 7 orbitals, so it carries a maximum of 14 electrons. Okay, so you see what I did there? Just multiply this number of orbitals by 2, and that predicts to you the number of maximum electrons you can carry in these subshells. Now what I'm saying is that you just put this up and down, 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 up and down. You're going to get 14 electrons in F. Up and down, up and down, up and down, up and down, up and down. You're going to get 10 electrons in D. Up and down, up and down, up and down. You're going to get 6 electrons in P. Up and down, you get 2 electrons maximum in S. Okay, which brings us to this page. So let us talk about the electronic structure comprehensively. We have determined that electrons live in orbitals, which are just the statistical spaces where you are likely to find an electron. Okay, that's what the definition of the orbital is. Electrons keep on moving around, so there's this random space where you're likely to find an electron. We call it an orbital. Okay, so this table shows you orbitals and electrons contained in their principal energy shells from n equals to 1 to n equals to 4. I told you that the s orbital carries a maximum of 2, so I'll write it again. S subshell carries a maximum of 2 electrons in its single orbital. We'll do up and down, those are 2 electrons. And then the P subshell has 3 orbitals. He carries a maximum of 6 electrons because each orbital carries 2 electrons. Okay, so he carries a maximum of 6 electrons. And then the D subshell has 5 orbitals. He carries a maximum of 10. He carries a maximum of 10 electrons. And then the F subshell has a maximum of 7 orbitals. Each carries 2 electrons, so the F subshell will carry a maximum of 14 electrons. And that is the math that's being shown down here. Whatever I wrote there is what's being shown here. Okay, looking at the fourth principal quantum energy level, principal quantum number, he has all the subshells S, P, D, F, and it will be the best for me to show you what's happening. So the 4s, 2 electrons. The 4p, it will be 3. Remember the 3 boxes? Each carries 2 electrons, so 6 electrons. 4d has 5 boxes, each carrying 2 electrons, so overall 10 electrons. And then the 4f, which has 7 of these, 1, 2, 3, 4, 5, 6, 7. Each of these will carry 2 electrons. We use those half arrows to show 2 electrons up and down. And 7 times 2 will give you 14 electrons. Okay, so now since we are trying to explain the electronic structure, let me start from now the first shell. Now remember what a shell means. That's the nucleus. The nucleus has these circles or levels going outside. So we'll call these n equals to 1, n equals to 2, n equals to 3, and then let me just draw n equals to 4 here. describing from n equals to 1 to n equals to 4. So what we are trying to describe here in this table is which orbitals are found in all these shells, n equals to 1, n equals to 2, n equals to 3, n equals to 4. So what I just showed you is what is found in the fourth principal quantum energy level, n equals to 4. So the fourth circle is this guy. He has a total of 32 electrons. Now, since n is equals to 4, 2n squared can also predict to us the number of total electrons in it, where n equals to 4, that is 2 times 16 equals to 32 electrons. So the fourth shell, which is the fourth level from the nucleus, n equals to 4, carries a maximum of 32. Now, can we do that for n equals to 3 here? Yes. The first time you see the F orbital is in the fourth shell. You don't see it in n equals to 3. In n equals to 3 is the first time you're going to see the D. The D is not found in the second shell. Now, the third shell obviously should have an S, should have a P, which is firstly seen in n equals to 2, and it should have the D now showing up. Okay, so each of the S carries 2 electrons. The S subshell only has 1 orbital, while we say the P has 3 orbitals. The P has 3 orbitals. And then the D, we said it has 5. And each of those will have 2 electrons, as I showed in the P. So if you count them, it will be 2 plus 6 plus 10. That's going to sum up to 18. Shortcut, 2n squared is 2 times 3 squared. It's like saying 2 times 9, and that is 18. Those 18 electrons are found on this third shell. Do the same math going up for n equals to 2, the second shell. Of course, you're going to have the 2s, and the first time you see the P is here. Like I said before, the P has 3 orbitals, and each of the orbitals, P orbitals, will be carrying 2 electrons. So 3 times 2 is 6. If you add up 2 plus 6, you're going to get 8. Use the formula 2n squared is 2 times 2 squared. That is the same as 2 times 4. That's going to give you 8 electrons in this shell. And those 8 electrons can be shown in pairs using dots like this. Okay? And then you are on the first one, that is only having an S. So just 2 electrons. N equals to 1, you can say 2n squared equals to 2 times 1 squared equals to 2 electrons, and we'll show it just using two dots. So that is how you can explain the electronic structure. I took time here on this slide because it's very, very important to know this, because you are building into explaining electronic configurations. So what we just did, we calculated the number of electrons in n equals to 1, n equals to 2, n equals to 3, n equals to 4. Like I said before, you want to start counting from the one closest to the nucleus of the atom. You're looking at the atom. So n equals to 1 is that, n equals to 2, n equals to 3, n equals to 4. So we said that n equals to 1, you have 2 electrons, 1, 2. N equals to 2, you have 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8. And the third shell, we said we have 18 electrons maximum in the third shell. And if you count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. And then in the fourth shell, you have 32. Okay, go ahead and count the outermost circle, the outermost shell. That's the shell of principal quantum energy level. Count the dots. They should be 32. Now, for your practice, let's work out an example. So we're going to say here you need to write out the orbitals in the fourth shell, just for the sake of it, practicing. Now we know that the fourth shell is n equals to 4. So there are two ways, just to summarize what we've done. You can use the formula, so it will be 2 times 4 squared. Why? Because n equals to 4. It will be 2 times 16. That gives you 32 electrons. That's one way. The other way is to start with the 4s, go to 4p, go to 4d. The first time you see the f is going to be in the fourth shell. This s will carry a maximum of 2, p carry a maximum of 6, d carries a maximum of 10, f carries a maximum of 14. You sum these up, you should get a sum of 32 electrons, which is what we did for this one. Okay, so the first time you see the S in the first shell, first time you see the P is the second shell, first time you see the D in the third shell, first time you see the F is in the fourth shell, and that is the drawing of the atom. So moving on with the electronic structure part 5, the S orbital has a shape, and usually it's spherical. The orbital gets larger size as the shell number increases. What we are saying here is that, yes, we know that the S orbital is spherical, but if this is 1s, in the second shell, 2s will be bigger, and then in the third shell, it will be even bigger as you go. So first point, know that S orbital is spherical in whichever subshell you'll find it, whether it's 1s, 2s, or 3s. The next point is the p orbital is a dumbbell shape. I usually say it's an 8 shape or infinite shape. So it depends on the orientation. If you draw what we call the Cartesian plane, if you draw the Cartesian plane where you have the x, y, z, that can tell you why we get to have different types of p's. Now remember, I told you that the p carries a maximum of 6 electrons. The p subshell carries a maximum of 6 electrons because he has 3 orbitals, and namely px, py, pz, and each of those can carry a maximum of 6 electrons. Those things I'm drawing, those electrons, those fishhook arrows are electrons. That's how we represent them in the orbital. Now if the dumbbell shape is on the x-axis, that's x, this is y, this is z. So if it's on the x-axis, then you call that a px. Now remember, I told you that first time you see the p is in the second shell, we always go 1s, and then probably you go 2s, then 2p. The first time you see the p orbital, or the first time the p orbital shows up, is in the second shell, the second circle, n equals to 2 outside the nucleus. So we are showing you a 2px, where 2 is just the that's the shell, and then the p is a subshell, and now we are saying the orbital is gonna be px. Okay, so the orbital is px, where the dumbbell shape or the H shape is on the x-axis. So now you know py is gonna be on the y-axis, and then pz is gonna be on the z-axis. There he is, he's on the z-axis cutting through. So each of these can carry 2 electrons, and for that reason we say that overall the p subshell carries a maximum of 6 electrons. I've emphasized that so many times. Now if you put all of them together, you're going to get them aligned or oriented 90 degrees, orthogonal we call it. They're gonna be 90 degrees orthogonal to each other's plane. That is the idea. So in summary, S orbital is spherical, P orbital is a dumbbell shape, shape of an 8 or an infinite, and depends on which axis it's lying. Okay, next we will talk about electronic configuration.